So let's get into the first video that actually has content, and so we're going to begin with propositional logic. This video is only going to contain just some basic definitions, no theorems, and also is a kind of like a big picture guide to how this is structured. We're going to start with syntax, and later we'll get to semantics for propositional logic. It's good to try to always keep in mind which things you are learning are syntax, which things are semantics, and kind of the glue between them. So that's a major theme, perhaps the major theme of mathematical logic. So it's always good to keep those separate, but also see the connections. So to be explicit, when we're talking about syntax, we're talking purely about the symbols, right? Without meaning, without interpretation, it could, right? Like the symbols could be meaningless as far, right? While we're doing syntax, and then the intention is that after we have developed the syntax, we can then attach it to meaning, and especially in this context, in some kind of very rigorous, systematic way. So anyway, the next few videos are going to be exclusively about the syntax of propositional logic, and again, this video is just some definitions, no theorems. But in the next video, theorems. Okay. So we're going to start building up a language, right? We'll call this a language. We're going to encounter a few different languages. This one, the propositional language. And one of its most basic constituents, again, purely as symbols, are this collection of symbols P sub n, right? So to be clear, P1, right? P1 is an element of this cent 0, of course, right? Not P0. My double struct Z with a superscript plus sign indicates the positive integer. So there's no ambiguity, right? Like if I had written the natural numbers, then you might wonder, do I regard the natural numbers as containing 0 or not? Well, to avoid the ambiguity, I don't have a belief about that, but to avoid ambiguity, I write Z plus. So P1 is in this set, not P0. And P2, P3, and so on, P a billion, and so on, right? All of those are elements of this set cent 0. We call this set the set of sentence symbols, right? Obviously, every element is a sentence symbol, okay? So and by the way, although we are not currently talking about semantics, it is worth knowing where that's heading eventually, right? Of course, those are going to be the symbols that we use to stand for so-called atomic sentences. So eventually, that's what we're going to call these things. And right, like they're supposed to represent like just a symbol standing in for a whole sentence, like the ball is red. And the intention is that these sentences really should not be decomposable into any smaller sentences, right? We'll see how to take them and build them up into bigger sentences, but these are the, so to speak, atomic units. And we combine them in order to build up bigger, more complex sentences. Okay. So anyway, moving on. We next have the symbols for the connectives. We will call this tail symbol the negation symbol, right? The name for it will be negation. Again, we're not interpreting it. We're just talking about the symbols. So although it will be a unary connective, we don't yet know in what sense, right, what it means really to be a connective. But in any case, so we have that symbol, the tail symbol, which we call negation. That's going to be a unary connective. And so we'll go ahead and just call it a unary connective. Then there are the binary connectives, conjunction, disjunction, conditional, if and only if, which is often abbreviated as I have here by IFF. And then we collect them all together into a set that I'm going to call con, C-O-N-N. And so that is our set of connectives. Now, this is everything we need for the symbol set in the language, right? So eventually, when we do get around to defining what the language is, it's going to be made up of sequences of symbols, right? That's going to be how we form our sort of like sentences and so on. But for now, right, like we can already say that, you know, what is the symbol set? What is the full set of all symbols that we will use to build eventually the sentences that we define? This is it. So it's just the sentence symbols together with the connectives. That's it, right? A lot of other systems, right, in a lot of other textbooks will also have to talk about parentheses and sometimes other symbols. This is quite nice. We're going to do this with prefix notation, and it avoids the need for parentheses. We'll see exactly how that goes later. But it really does simplify the treatment, so it's nice to do it this way, and proofs just go more easily. So anyway, this is the full symbol set. Okay. I'm now realizing that what I wrote earlier was not showing on the screen. But anyway, so hopefully that's clear. Okay. So, right, the next topic is joining symbols, right? So we know the symbol set. Now we're going to say that an expression, more fully an L expression, is any sequence of symbols from our symbol set. And our symbol set is denoted by this symb sub L. So any finite sequence of the symbols is an expression. I'll certainly get lazy and not always say L expression, so you just understand that whenever I say expression, I mean an L expression. So presumably from like a background in discrete mathematics, you already know about sequences, right? And especially finite sequences that can be formed from any set. Well, this time we're forming it from the symbol set. So since expressions just are sequences, then the length of an expression obviously is just going to be the length of the sequence. If we want to join two expressions together, right? Alpha is an expression with length m, beta is an expression with length n, then we can talk about concatenating those expressions where we just write alpha next to beta, and what that means is the L expression with first all the symbols from alpha and then all the symbols from beta. So all of this is fairly simple. Although we really don't have enough to make an interesting exercise, every time I introduce something, I like to try to make it an exercise just to kind of use these ideas. Well, I can't make an interesting exercise with so few ingredients. So here's a dumb exercise. So if alpha has length m, beta has length n, right? These are L expressions. What is the length of alpha beta, the concatenation? Well, normally I would pause and encourage you to work it out on your own before looking at the answer, but of course this is too easy for that to really be worthwhile, right? Of course the answer is m plus n. So, okay, let's go on to another exercise, maybe one that's slightly more interesting. Can we decide from the definition so far whether an expression of length 0 exists? Well, presumably, right, hopefully an earlier class in discrete mathematics talking about sequences has established that a sequence of length 0 exists. It's basically like the empty set, has nothing in it and so on, but it does exist. So since sequences of length 0 exist, then the expression of length 0 is just the sequence of length 0. So yes, right. The answer is yes. sequences of a length 0 do exist. We'll call them the empty sequence. Okay, moving on to the next thing. We're going to head toward defining this notion of sentence complexity, or as the book calls it, sentence level, right? So level, complexity, they're synonyms. To help me to sort of express this, I'm going to create a little notation. So this notation says that if dot is any symbol, right? So dot is kind of like a variable, and it could be any symbol. And if I write it next to x, which is a set of L expressions, then what I mean by that is the set where the dot is concatenated with every expression from the set. So just to give a quick for instance, what if I took negation applied to, let's just say the set of negation and P3, then I just concatenate that negation with every element of the set, right? Not all of these elements are meaningful things, so I'm just demonstrating what this notation means. I'm not applying it in any interesting way just yet, but that's just a demonstration. Anyway, we'll also define this other similar notation where, again, dot is any symbol, x and y are two sets of L expressions, and this is defined somewhat obviously, I suppose. Where we concatenate the dot with an expression from x with an expression from y. That's what this notation means. So now that I've established that notation, let me go ahead and use it to define sentence complexity, or at least we're heading in that direction. We're not there yet. So I'm going to define this set, sent n, and I'm going to define it for all of the positive integers. We already know what it is for 0, right? That's been defined already. So I'm going to now extend the definition for every positive integer n in the following way. First of all, it's going to inherit every sentence from the previous set in the sequence. So, what you can kind of imagine this leading toward is that I'm going to develop, right, like sent n is going to be the set of all sentences of complexity at most n. Not exactly n, we'll get to that in a minute, but sent n is every sentence of every complexity from 0 up to n. So it's inheriting all of the earlier sentence complexity levels. Then I put it together with, right, to get the more complex sentences, I take the negation of sent n minus 1, right? So this is how all the negations of sentences get into ultimately what will be our total set of sentences, right? So if you had the sentences of a lower complexity level, by negating all of them, we get the sentences of a higher complexity level. Now, in a similar way, although I want to be a little bit lazy, so to speak, and use some abbreviated notation, so I'm going to, again, let the dot symbol be like a variable, this time ranging only over the binary connectives, so these symbols, and we'll form all of the conjunctions, disjunctions, and so on, and take all of them and put them into our set sent n. And this is everything, right? So this is what sent n is. Sent n is the previous sentences together with their negations and all of their binary connectives built up. So anyway, so there is the definition of sent n. Let's do a little exercise, right? I've basically already done something just like this a minute ago, so of course, right, if this is just an exercise in using my little made-up notation just to make sure that it's clear what it means. So I think the right exercise number 3 should be fairly obvious and probably doesn't need a lot of explanation. Exercise 4 is maybe a little bit more interesting. So here we want to, it's very open-ended, right? I'm not really being precise about what I mean by this, but let's just try to get a better handle on what this particular set looks like. So, so really, I'm just going to describe several elements in the set. So I've got conjunction sent 0, sent 0. Now, of course, by definition, right, with this taking the role of the dot in my notation, and this being an x, and this is y, right, in that dot notation established earlier. By definition, this is the set of all conjunction EF such that E is an element of sent 0, F is an element of sent 0, right? And, you know, right, we could maybe even do better or be more descriptive and say that this is actually the same thing as PI, PJ, right? Because every element of sent 0 has the form PI for some positive integer I, and likewise said all over again with J. So we could say such that I and J are any positive integers. So there's the description, right? And you know, perhaps if this is at all helpful, right? This is an element of that set, right? Just to give a for instance, right? So, so hopefully it's clear what this set is. Okay, one more exercise, and this one perhaps even more interesting, if any of these were interesting. We're going to find the smallest n such that this, right, conjunction negation P1, P2, that thing is in sent n, right? So we're seeking the minimum n for which this is true. So let's just go in order, right? Let's just think about n equal to 0. Could that possibly be the answer? Well, no, this element is not in sent 0 because sent 0 is made only of the sentence symbols, and this is not just a sentence symbol, so it's not an element. So 0 is not the answer. Let's move on to 1. Could this be in sent 1? Well, to give a somewhat quick version of the argument, I guess maybe if my quick version is too quick, then leave a comment. Maybe I'll make another video or just explain it in the comments or something. But anyway, to give the quick version, if this is in sent 1, and remember, sent 1 by definition is sent 0, right? Here n is equal to 1, and so this index is given by n minus 1, which in this particular case means 1 minus 1, which is 0, of course, right? So is sent 0 union, negation sent 0, union all of these guys, and so, we already know that if this expression is in sent1, it must be in one of these sets. We've already said it's not in this set, so there's just no way that that's where it's coming from. Also, every element of this set leads with a negation, and our expression does not lead with a negation, it leads with a conjunction. So it also can't be coming from that set, and therefore it must be coming from this set. And we could do a similar exercise and demonstrate that it can't be coming from the case where the dot takes the or, right, because the expression would be leading with an or symbol, ours is leading with an and symbol. So it can't be that one by the same reasons, it can't be either of these. So where I am up to this point is I have established that if, right, kind of like a proof by contradiction, if conjunction negation P1, P2 is in sent1, then it must be in conjunction sent0, sent0. Right, that is effectively where my argument is up to this point. And then I want to argue that this is not possible, and then my proof by contradiction is done, right, where I'm effectively arguing that this expression is not in sent1. So how do I know that this cannot be true? Well, you know, it certainly leads with a conjunction just like these do, so that's not the issue. But what is the issue is that whatever comes after the conjunction must be some two concatenated elements of sent0, which is to say a concatenation of some two sentence symbols. But no matter how you parse it, what comes immediately after the conjunction in this particular case cannot possibly be a sentence symbol, because it leads, right, whether you parse it as just the negation, which, I mean, right, if you want to be very technical and think about ways that this could get parsed, you could parse, right, you could try to investigate whether that's an element of sent0 and that's an element of sent0. Well, clearly that's not true, right? I take it that's clear. Or you could say that this is an element of sent0 and this is an element of sent0, but that's also not true because this is not an element of sent0. So anyway, maybe I'm belaboring the point, but I take it that that is a convincing argument that this expression is not in this set, and so that's kind of concludes the argument that n cannot be equal to 1. Now we'll move on to 2, and it will turn out, I think somewhat predictably, that the answer is yes, that this is an element of sent2, and as soon as I'm done showing that, it will have established that the answer to this question is n equal to 2. So how do we know that this is an element of sent2? Well, you know, it is fairly easy, and I'll leave it to the viewer to prove that negation P1 is an element of sent1. If that's not clear, leave a comment and I can explain more, but it's a good exercise to make sure you understand why that's true, so try to work it out for yourself. Also, P2 is an element of sent1. And then by definition, right, that you can put this together to say, or to conclude, or to infer that, conjunction negation P1, P2 is an element of conjunction sent0, sent0, sorry, sent1, sent1. And this is one of the, right, this is one of the sets that is in the union that defines sent2, right? So since this effectively is a subset of sent2, then the proof is complete. So we ruled out 0, we ruled out 1, we proved that 2 does hold, and therefore the solution to the exercise is n equal to 2. Okay. We can now move on to define the entire set of sentences in the language. We'll denote it by sent sub L, and it is given by just unioning all sent n for n greater than, an integer greater than or equal to 0. So that's my notation here, the double struct z subscript greater than or equal to 0. That is just explicit notation to emphasize that that these are integers and that it can take the value 0. So this is the definition of our set of sentences. Of course, every element we will call a sentence. And at this point, we can also define the complexity or level of a sentence. And in fact, it's basically the same thing, right? Or it's you know, a generalization of the exercise that I just walked through, where you find the minimum n such that the sentence is in sent n, right? In fact, I even like to sort of express this with a capital theta as a function, right? So capital theta is a function. The domain is the set of all sentences. The codomain is the set of non-negative integers. And it is defined by theta of phi is the level of phi, right? It is the minimum n such that phi is in sent n. And notice, by the way, that every sentence must have some level, right? Because if it is a sentence, it is in sent L, therefore it is one of, right, it is in one of the sets in the union, which means that it's in some sent n, right? So every sentence has a level. Okay. And that's the end. So in the next video, we'll start stating and proving some basic theorems on syntax.